Hi everyone, this is my video on resting potential, local potential, and action potential. So in this first picture here, you will see that there is a neuron, and outside of the neuron is the extracellular fluid, which is also known as the ECF, and it contains positively charged sodium ions. And inside the neuron, there is the intracellular fluid, also known as the ICF, which contains positively charged potassium ions and large protein anions that cannot be moved out. And we will move over to this picture here. So there are two gates in the resting potential, the sodium gate and the potassium gate. So at the resting potential, the neuron is at rest and is capable of and ready to send a signal down its length. And the ICF has to be at a negative 70 millivolts. So then we will move to our local potential. So there will be a stimulus that is reached at the dendrites, which will then move to the soma and then moved to the threshold, which is at the axon hillock. And at the axon hillock, the signal needs to be at a 15 millivolt difference, so from negative 70 to negative 55 millivolts in order for it to be moved down the axon. There are three characteristics with local potential. Graded, they vary in magnitude depending on the strength of the stimulus. The more stimulation that occurs, the more sodium channels will open and the more sodium ions will enter the ICF, depolarizing the membrane to a greater degree. Then decremental, the current gets weaker the farther away from the site of stimulation it gets, and it is reversible. So if the stimulation stops, the membrane will return to its resting membrane potential. This is due to the fact that the sodium gates will close again without stimulation, and the pumps can return the sodium ions to the ECF. So then we will move to our action potential. So at the action potential, it follows a all or none law. If the local potential that reaches the hillock is strong enough to trigger an action potential, the action potential will occur at full strength, and if not, no action potential occurs. So the stimulation is reached at the dendrite, to the soma, to the threshold, then down the axon. So there are three characteristics of action potential. Action potentials are not graded, and they are non-decremental, so the action potential maintains their full strength down the entire length of the axon regardless of distance, and it is irreversible, so once an action potential starts, it cannot be stopped. So then we will move on to our first step, which is depolarization. So once the threshold is reached, the abundant sodium gates in the membrane of the hillock open rapidly, and sodium ions from the ECF diffuse into the ICF. This causes the membrane potential to undergo the rapid depolarization that will see the value of the ICF go from a negative 55 millivolts through 0 millivolts and then up to positive 35 millivolts. And then at positive 35 millivolts, which is the peak value of the action potential, the sodium gates will close, and then the potassium gate will open, which is caused to undergo repolarization. And then when a value of negative 70 millivolts is again reached, the potassium gates close with both gates. The potassium gates close, and then with both gates closed, the sodium and potassium pumps are able to return the cations to their original locations, allowing the membrane to recover and to be ready to do everything all over again. So in this picture here, you will see that now that the sodium gate is closed, the potassium gate is open, and those potassium ions will then diffuse into the ECF.